Good afternoon and welcome at yet another interesting talk here at the Technical Forum at Hydrogen Fuel Cells Europe at Hannover Messe 2023. I just made the mistake of saying 2022. I'm not going to do that again, don't worry. We have an interesting topic here, so I would suggest to get comfortable. People in the back standing over there, I see you. These seats are more comfortable than the ones you have at home, and we have drinks on the house. So it's a win-win situation, and I would definitely make my way up here. On stage, we'll be talking about pressure regulators for hydrogen and fuel cell applications. Interesting for 99% of the people here, I think. So yeah, stay seated. And please welcome to the stage Pressure Tech, and then specifically the Business Development Manager for Hydrogen and Fuel Cell Market, Jack Samways.
Good afternoon. Thank you very much for joining. My name is Jack Samways. I'm the BDM for the hydrogen market here at Pressure Tech. A bit of background about me. So across my 2 degrees, I focus my research in hydrogen. So my undergrad, hydrogen fuel cells, and focus my efforts on hydrogen production, my postgraduate. So I was brought into the company to develop the industry, use my expertise to kind of work closely with the hydrogen companies, and develop the industry for Pressure Tech. So first of all, why hydrogen? Why are we all here today? Within the next 10 years, we will reach 1.5 degrees of warming. That's an inevitable. What we can do, and why we're all here today, is to limit that even further. So why hydrogen? Hydrogen has to be a key contribution to solving climate change. It won't be the whole solution. It has to be backed up by renewables, by electrification of the grid. But hydrogen must be realized its potential. And we look at the electric grid behind me. Here at Pressure Tech, our experience in the energy market has made the transition to hydrogen seamless. So when we began to start within the hydrogen industry, we want to cover as many bases as possible. So that includes electrolyzers, compression, storage, distribution, and distribution throughout fuel cells and ICE engines. So that's our main focus at Pressure Tech. Why pressure regulators? Pressure regulators are mechanical devices that take a large pressure to a small pressure. There are 2 types of pressure regulators: back pressure regulators and forward reducing pressure regulators. Back pressure control upstream pressure, and forward reducing control downstream pressure. The 4 factors that go into the design of a regulator: inlet pressure, outlet pressure, media, and flow rate. As you can see from the diagram, if it's going to load. So if we take for an example of a hydrogen application, 350 bar is the inlet pressure or storage pressure. The outlet pressure could be 10 bar. The media, obviously hydrogen. And the flow rate, perhaps 5 grams a second. As the pressure regulator is compressed to spring, you will build up the outlet pressure. So this is the application that's required across fuel cell applications, ICE engines, refueling stations, and of course electrolyzers for back pressure regulators. Bit of a technical difficulty, maybe. Sorry, could we change the slide, please? Sorry about this, guys. There we are. OK, so we just leave it there. So the blue line is the inlet pressure at 350 bar, and the red line is the downstream pressure of 10 bar. There we are. OK, so going back to the hydrogen economy. Sorry for that blip. So starting on the left, we have production. So these are back pressure regulators for electrolyzers. And then in terms of dispensing or refueling stations, you use the RF1034, which will take 1,000 bar down to 350 or 700 bar. And distribution, we're talking about fuel cells, ICE engines. These 5 pressure regulators here, they're used for a variety of flow rates, a variety of inlet pressures. And these are what you'd have for the distribution to bring the pressure down to a usable pressure for the fuel cell or ICE engine. Beginning with electrolyzers or production. So what is electrolyzer? I'm sure you guys have heard it all here before. What it is electrifying water to create hydrogen and oxygen. So the electrolyzers all here today, they'll require back pressure regulators to control this pressure being produced. So both the hydrogen and the oxygen require back pressure regulators, usually around 35 bar. What will vary is the flow rate. Now, the flow rate defines the CV size of the pressure regulator. So the CV size relates to the orifice size of the pressure regulator. So a 1 megawatt electrolyzer may use 500 liters per minute, and a 2 megawatt electrolyzer may use 1,000 liters per minute. So this is how it kind of varies in that sense. Dispensing, so refueling station. Now, as the hydrogen industry has evolved, we found that design standards and certifications have become especially paramount. For the design of pressure regulators, there's two main standards, SAE J2601 and ISO 19880. SAE J2601 is the diagram behind me. That covers everything before the nozzle and how it affects the main basis behind it. It prevents overpressure and overheating. The pressure requirements for 350 bar systems is 438 bar, and the maximum pressure for 700 bar systems is 875 bar. In terms of temperature, the minimum being minus 40 degrees, and the maximum being plus 85 degrees. So this is the factors that go into the design of a pressure regulator. It also defines the flow rates, so 60 grams a second, 120 grams a second, and 180 grams a second. What we're also seeing is the demand for faster and faster refueling as the demand for refueling stations also increases. So we're seeing a flow rate of 300 grams a second. And this also affects the CV size of the pressure regulator. Now, our pressure regulator, shown here, has been designed to be responsive enough to stay within what we call the pressure corridor. So the diagram on the right defines the maximum and minimum pressure. So say you're refueling a vehicle at 300 bar, so the maximum pressure can be at that point is 370, and the minimum is 275. So our regulator is responsive enough to stay within those parameters of this pressure corridor. As you can see, the RF1034 pressure regulator there. What goes into the design of the valve is defined by the ISO 19880 standard. So this defines the strength, torque, and leakage values of this pressure regulator. Regarding the strength values, the maximum pressure that the regulator can take is 2.4 times the maximum working pressure, which is over 2,500 bar. So this regulator is designed, it's over-designed in terms of being, if any catastrophe could happen in the refueling station, the regulator will withstand that pressure, withstand the hydrogen. Moving on to the buses and trucks. So we've designed the Auto 438 pressure regulator to be designed and fits onto a hydrogen fuel cell vehicle. If we could do the thing. Anyway, so this will take 350 bar down to 10 bar for the fuel cell. It's situated downstream of the hydrogen cylinders and upstream of the fuel cell. Now, the certification that's required to sell this pressure regulator for these hydrogen fuel cell vehicles is called EC79. EC79 is a certification that it now allows the hydrogen to go through 90,000 cycles of testing, which equates to 10 years life cycle. Alongside that, the shell pressure, the leakage pressure, all of these factors go in to make sure this design is very robust. There is a diagram that hopefully will be played in a sec. If not, no worries. Just showing where the regulator sits within the hydrogen system. Finally, the first pressure regulator we ever developed was the LW351. It's a lightweight regulator that fits onto drones. So the drone market was using electrolyzed before, electrified drones now, and now they're using hydrogen drones to extend the range of this. So our pressure regulator weighs only 200 grams and brings 350 bar down to half a bar. So as you can see from the diagram, the pressure regulator stays on the drone, whilst the CV4 cylinder valve, which works as a check valve, stays with the hydrogen cylinder. So this allows really quick and safe refueling, as well as minimizing the downtime when I want to get the drone back in the air. So you can change over the bottle with another cylinder valve that screws onto the pressure regulator. Once it screws on, the hydrogen can be seen and the drone goes back in the air. When it comes to refueling, you can use our refueling nozzle to quickly and safely refuel the hydrogen cylinder without the need for check valves, hoses, pipes. So this refueling nozzle screws onto our cylinder valve, and this connects to a larger volume cylinder and can refuel a small-scale drone, boat, or bike cylinder with ease. So that's the system, the LW351 on the left, and the CV4 cylinder valve on the right. Thank you very much for your time today. We have a booth at F25, and welcome any questions, but thank you very much.
Thank you, Jack. Wonderful presentation. And I think we still have time for some questions from the audience.
Any questions
we
at
still
all?
have 5 minutes. So are there any questions? No questions. Okay,
Well, if not, as I say, F25, you're welcome. We're here all week. Any questions, we'd be glad to help.
Okay, perfect.
Thank you very much.